Hello, everyone. It's really pleasure to have in the Frame Mobility Research Institute Dr. Lynette Cheah, that is an associate professor of engineering systems at the Singapore University of Technology and Design. She directs the Sustainable Urban Mobility Research Laboratory, which develops data-driven models and tools to reduce the environmental impacts of passenger and urban freight transport. She's an associate editor for the Journal of Industrial Ecology and review editor for the UN IPCC, I'm not sure what it stands for, six assessments report. I would like to thank you all for your participation, and also I would like to thank the WTS Women Transportation Seminar at the Florida Atlantic University that they put this webinar together. Lynette.
Thank you, Professor Kaiser. Thank you also to Vasya and Lini for having me here. So very grateful to have this opportunity to share with you more about the study that we're doing. So actually the IPCC stands for the Intergovernmental Panel on Climate Change. So just to clarify at that point, I apologize. Maybe I shouldn't have used the acronym, but I've had a role in the climate change panel that pushes out all these reports on the state of climate change, and there's this one chapter there on decarbonizing transportation. That's the chapter that I've been contributing to. It's related to today's topic. So today I wanted to share about life cycle emissions associated with medium-duty commercial trucks. And I'd like to acknowledge that this is joint work with one of my students, Li Wei Yao, as well as a researcher, Yu Ting, in my team. So let's jump in. I hope to clarify a bit because when I first shared the abstract with Vasya, I had mentioned in the title that this is a study looking at the life cycle greenhouse gas emissions for heavy duty trucks. I have to clarify that heavy duty trucks in Singapore is considered medium duty in the US. So knowing that the audience here is mostly based in the US, maybe this definition should be offered a bit upfront. So we're looking at commercial trucks with a gross vehicle weight between 3.5 to 7 metric tons, so that's 1,000 kilograms. So this is the most common type of heavy goods vehicle found in Singapore. So we call them heavy goods vehicles, but I think in the US, it's more known as class 3 medium duty trucks. In the European Union, it will be recognized as a category N2 commercial trucks. So just wanted to clarify that, and I hope no one in the audience is too disappointed that we're not dealing with this very big trucks at all. But these trucks still play an important role, and let me introduce that a bit more. So road freight is a key sector that we're trying to decarbonize in parallel with decarbonizing passenger transportation. Almost all road freight right now runs on diesel fuel, and the demand for freight is rising and growing very rapidly. So it's definitely a growing source of oil demand. In Singapore, commercial vehicles, or these goods vehicles as we call them, make up about 3/4 of the diesel-fueled vehicles, and they make up about 19%, or 1 out of 5, vehicles in Singapore are diesel vehicles, and they're responsible for, even though they're a small fraction of the total vehicle population, they're responsible for a significant portion of greenhouse gas emissions from road transport. So that's about 63%. So we see an opportunity here. Can we think of alternatives that we can switch out the use of diesel for road freight? So that's what we're considering today. So in decarbonizing road freight, which is the topic, with the country or the city, I don't know if any of you are familiar with Singapore. It's a very small city-state in the tropics, just south of Malaysia, located in Southeast Asia. So we aim to phase out internal combustion engines by year 2040. For passenger vehicles, I think this is quite readily underway. The movement towards electrifying passenger vehicles is really gaining momentum. But for medium and heavy duty trucks, it's much more challenging. There are not as many obvious alternatives, partly because of the high mileage and the payloads that they have to ferry. So the impacts are not yet fully well understood. There are studies looking at hydrogen fuel cell trucks as one of the alternatives, but there are not that many of them. And even if the studies that exist maybe only focus on some aspects of the entire life cycle of the vehicle. So we see a gap here that I think deserves some attention. We also understand from existing studies that life cycle impacts of these alternatives tend to be very context specific. So we do need to look at the specific use case, the market that these vehicles are in, how they're used before we can make a proper assessment. So here, some images on the slide right now show the battery electric concept vehicle on the left, as well as a hydrogen fuel cell vehicle on the right, both by Mitsubishi, just to demonstrate what it would be like, what it can be like if we were to replace conventional internal combustion engines with these alternatives. So we take on a life cycle approach. And so what is a life cycle assessment? Some of you may already be familiar, but just to recap, it's a tool to help us look at the environmental impacts of a product or a system or a service throughout the entire life cycle. So we will be accounting for all life cycle stages from the raw material processing to producing the product to distributing it, using it, and then dealing with it at the product's end of life. So this life cycle perspective is helpful because it helps us to look at the impacts of alternatives relative to baseline or the best practice today. And we take that approach because we are interested to avoid the issue of problem shifting or creating new problems as a result of the introduction of an alternative. So the ISO has come up with a framework for how life cycle assessments can be conducted. It usually begins with a goal or a scope definition where we define why are we doing the life cycle assessment, who does it serve, what should we include or not include within the scope, and then after that, a very careful inventory analysis. So inventory analysis would account for the material inputs or resource inputs into all the different life cycle stages that's considered within the scope. What are the emissions? What are the wastes or byproducts? Or what is the end product? And then some inclusion of the impact categories to consider. So for today's topic for the trucks, we're looking at greenhouse gas emissions, which concerns climate change. But there are many other impact categories like impact on human health or ecotoxicity. So there are different categories that we can think of for the specific study of interest. And then throughout that, we will be interpreting the results and again, considering who is the audience, what purpose does the study serve, be it for design improvements or for policy making, for marketing, and so on. So for the purpose of our study, which is to look at greenhouse gas emissions for trucks, these are the alternatives that we will be considering. We're looking at the conventional diesel, and we'll be comparing hybrid diesel to that, as well as a battery electric truck and hydrogen fuel cell truck. So we've actually selected these alternatives because we think they're the most promising in Singapore's market. So we did not consider others like, for example, natural CNG vehicles or biodiesel. Yep. And then again, we're looking at these medium-duty trucks weighing about 3.5 to 7 metric tons. We're looking at the case of Singapore, where it's a very dense urban environment. We don't really have a lot of renewable energy alternatives, energy sources available, so a little bit constrained in that context. We will be measuring the greenhouse gas emissions on a life cycle basis on a per ton kilometer metric. So this is per ton and kilometer traveled, right? So this is the utility or the service that the trucks will be performing. In terms of data, the life cycle assessment studies are very data hungry. So we will be using existing LCA databases such as GREET that's offered by Argonne National Lab. We'll be using some of the information from existing literature, past LCA studies. Wherever available, we'll try to use the local data. Yeah. The figure on the right shows the scope. that this study is undertaking. So when we think about trucks, it's bringing together actually two products. You have the fuels that have to be produced, and it goes through a chain of activities, like the feedstock has to be produced, it has to be transported, and then eventually distributed, be it diesel, electricity, or the vehicle itself has to be manufactured, assembled, transported to the end user. And during the use phase, which is in the middle over here, or the tank to wheel portion, the vehicle is it's operating, it's being maintained, and then eventually reaches its end of life and will be disposed. So let me break down these three stages of the life cycle a little bit in more detail. So here's a distribution of the goods vehicles in Singapore by weight categories as well as the body types. So just wanted to set context that we're focusing on this part, the kinds of vehicles that's more prevalent in Singapore. So these are the ones weighing 3.5 to 7 brake tons, having a body type that looks a little bit like the one over here. So it's either open top or enclosed box kind of trucks. Yeah. So in terms of the vehicle cycle, so this is the portion where we are looking at the manufacturing of the vehicle itself. The chosen body type is the Mitsubishi Canter, which is a very common heavy goods vehicle model here. So notice that in any LCA study, again, for your context, you'll be looking at the typical vehicle types. We've selected equivalent models for each powertrain of interest. So this would be the hybrid electric vehicle as well as the fuel cell vehicle. For a fair comparison, we've made sure that the specifications and the configurations of these vehicles are similar, so similar power output and performance across these alternative powertrains. And during the modeling process, we assume that they're carrying the same payload. So greenhouse gas emissions are emitted during the vehicle cycle when we're manufacturing the vehicle. You can also get credits when you're recycling the vehicle when it reaches its end of life. So we'll have to account for all the key vehicle components like the body of the vehicle, the battery if for the hybrid or the electric vehicle, the fuel cell unit, as well as the hydrogen tank for the fuel cell vehicle. Most of these emission factors are obtained from the literature where available, such as, for example, for battery capacity, so the kilograms of CO2 equivalent emissions per kilowatt hour of battery capacity. So we'll have that factor and we'll account for that based on the specifications that we've chosen. We've also accounted for component replacements for electric vehicles. You might have to replace the battery every 2,000 to 5,000 cycles. So that's accounted for. Fuel cell unit also has some limits, and then we've counted for the operating hours that it can accommodate before it needs to be replaced. For the fuel cycle, we need to break it down further into the different pathways, again, depending on the powertrain that we're looking at. Diesel, electricity, or hydrogen have to be produced. So let's look at diesel first. So crude oil has to be, extracted, transported, refined before it eventually becomes diesel that we can use at the pump for the trucks. For electricity, in the Singapore's case, the electricity grid is very heavily reliant on natural gas. So still fossil fuel based, predominantly fossil fuel based, but it's a cleaner form, natural gas. And more than 90% of the electricity now is generated by combusting natural gas in these combined cycle gas turbines. This natural gas is either piped into the country or shipped in through liquefied natural gas terminals. So let me show you the next chart that shows Singapore is located here in the southern tip of the Malaysian Peninsula. And then the gas can be either piped in from neighboring oil fields in Malaysia or Indonesia. So these pipelines run hundreds of kilometers into Singapore. Or shipped in through these tankers like you see in the bottom figure over here. So liquefied natural gas accounts for about 1/3 of the natural gas that we use to generate electricity. About 2/3 comes from pipes. If we look at hydrogen production is a little bit the most likely fuel pathway that it will pursue will likely be steam methane reforming, which is how most of hydrogen produced now relies on this process. So steam methane reforming involves producing hydrogen from natural gas, and the overall reaction, it results in both hydrogen production as well as CO2 emissions. It's known as gray hydrogen if it's still produced using fossil fuels. So we could have this pathway shown at the bottom where hydrogen is produced through SMR and then subsequently compressed into either gaseous hydrogen or compressed and then liquefied to liquid hydrogen. Okay. We also inserted one fuel pathway which is reliant on renewable energy. So we thought that this would be interesting to illustrate the full potential if we were to be able to, decarbonize our electricity grid and then rely predominantly, actually entirely on renewable energy. So solar is the most promising option for renewable energy in Singapore. So we've inserted this solar possibility here. So solar can help produce electricity or can help with hydrogen production as well. So we're still far from this possibility right now. Solar penetration is only about less than 5% in Singapore. It's very difficult to grow given the limited land space that we have. But again, considering this just as an illustrative option. For the fuel cycle, we've also accounted for some of the losses that might happen during the transmission, distribution, or refueling. And then we've used some of these factors of losses from existing data sources like GREET or the local energy authority to reveal to us what's the grid emission factor. So that's the CO2, kilograms of CO2 emitted per kilowatt hour of electricity produced. Right, so that was the fuel cycle. So let's look at the use phase, and also known as the tank to wheel impact. Here, the first thing we did was try to construct a representative drive cycle for Singapore trucks. And we did this by making use of some engine data that we managed to collect from 5 trucks that were making urban deliveries, retail deliveries actually in Singapore in 2015. So with we made use of a data logger called an onboard diagnostic logger that you can sort of plug into the OBD port within the truck and then extract out the engine data. Very high resolution, second by second engine as well as GPS data was collected. This helped us to extract the trips that were made by the trucks during the times that they were tracked. And then we managed to use the sort of aggregate all the trips that were monitored into a representative drive cycle that sort of reflects the kinds of operations that the vehicle goes through in Singapore. So again, you can see how we've tried to bring in the local use and the context for which the trucks are used in our analysis. So the bottom right chart shows a speed time trace, which is the drive cycle of the vehicle. Average speed was only about just under 30 kilometers per hour, primarily because of a very long idling time. So trucks might also be idling during the deliveries that they're making. As they make their stops, they could be idling. Some of the idling might also happen in urban traffic conditions. So that might explain some of the long idling tail that we see over here. We also built some physics-based energy consumption models to reflect the power demand as well as the total tank-to-wheel energy consumption for these alternative powertrains. So by looking at the forces acting upon a vehicle, those are all accounted for. We looked at the speed and acceleration as well as the mass over the constructed drive cycle. We've also accounted for the energy recovery that would occur in hybrid electric vehicles as well as the fuel cell vehicles. And ultimately, we got this chart at the bottom right, which shows the tank-to-wheel energy consumption on a per ton kilometer basis for different payload settings. This chart over here shows an average payload setting of 1.4 tons, which is about 50% of the capacity for the different powertrains. You can already see, compared to the conventional diesel, which is shown on the left, the battery electric vehicle offers some advantages over the tank to wheel in terms of energy consumption. So that can be reflected eventually when we account for the greenhouse gas emissions. Right. For the use phase, we also have to consider the lifetime mileages. So we made use of, again, some information or data on the daily mileage for trucks in Singapore. So this was, again, another data collection effort that we had happened to be able to perform. And you could track the daily mileage from this sample of both medium as well as heavy duty commercial trucks back in 2017. So we discovered that, trucks travel on average about 100 kilometers per day. If you multiply that by number of weekdays in a year, as well as the average lifetime, the average lifetime actually it has a very strange distribution that you see on the right-hand side. So this shows the distribution by age on the horizontal axis and the proportion of vehicles that are scraped on the vertical axis. So this is actually a function of the vehicle ownership policy. So Singapore has very strict ownership policies. I'm not sure if you're aware, but it's a very high tax on ownership, and this certificate of ownership that you can purchase is valid for 10 years, after which you have to scrape the vehicle. That's why we see this peak at 10 years. Many vehicles scraped at this point. If not, you can pay a sum to renew that ownership certificate for 5 years or 10 more years, and that's why again we see the peaks at 15 years as well as at 20 years. So the average age is about only 14 years, fairly young fleet, getting us to a total lifetime mileage of about 388,000 kilometers for trucks. So this is the input that we'll use in our LCA study. So here we get at the results. So we've talked about the fuel cycle, we talked about the use phase, we talked about the manufacturing of the vehicle. So we have all the components we need within our life cycle assessment scope. So we arrive at the results. So here's a result that shows the life cycle greenhouse gas emissions on a kilograms of CO2 equivalent per ton kilometer basis. And we have that for the different powertrains shown at the bottom. So each bar is a different one. The one on the left most is the conventional diesel, which is our base vehicle. And each of these bars are broken down into the different life cycle stages as shown in the different colors. So the red one shows the use phase, direct fuel inputs. The green one shows the fuel production impacts. The blue shows the vehicle production impacts. Then the sliver, the purple sliver, actually shows the recycling credit at the vehicle end of that. But these are very, very small. So we already observed some things, right? One of the things that we can immediately see already from these results is that the fuel cycle or the fuel cycle is a really important part of the total emissions. So energy use in the use phase accounted for more than 75% of the life cycle greenhouse gas emissions based on the current fuel production methods. So it's really critical to consider, where's the fuel coming from? What can we do to decarbonize the fuel production if we wanted to decarbonize transport at all? So decarbonized fuel production pathways have the lowest life cycle greenhouse gas emissions. So these would be the options which rely on things like the renewable energy sources. So the battery electric vehicle that's powered by solar power exhibits the lowest greenhouse gas emissions on a life cycle basis, as with the fuel cell vehicle that relies on hydrogen that's produced using solar, right? So this was done for an average payload of 50%. We did the same calculations for different payload levels. You could have payloads at 25% or payloads at 75%, and then the greenhouse gas emissions, again, on the per ton kilometer would vary accordingly. But we didn't see much variation in the relative positions of the alternatives. So it's just the quantum changes, but the relative rankings of these alternative powertrains do not change too much. Yeah. If we zoom into the options that we can sort of use that sort of relies on the existing fossil fuel-based methods now, meaning if we continue to and not expect to green our grid or decarbonize our grid, diesel hybrids and fuel cell vehicles using gaseous hydrogen via steam methane reforming would be the options to consider. So hybrids would offer about 8 to 10% greenhouse gas reductions across all the different payload variations. So that's the differential between here the conventional diesel versus the hybrids is the second bar shown over here. So some reductions, 8 to 10%. The fuel cell vehicles with gaseous hydrogen would give us about 10 to 25% reductions in life cycle greenhouse gas emissions compared to conventional diesel. For battery electric vehicles, we were quite optimistic for electrifying transport, right? Especially for passenger transport, we're quite optimistic. But for freight, as it seems, we found mixed results. So they did not always resulted in reductions in greenhouse gas emissions. So the electric vehicles powered by the current electricity mix, which is again predominantly reliant on natural gas, had unclear reductions, sometimes a reduction of up to 13% greenhouse gas reductions, or increase by 6%. So much of this uncertainty arises from the battery production impacts, as well as the replacement that might be needed to sustain the use of the vehicle over its lifetime. If we were to use fuel cell vehicles with liquid hydrogen and using steam methane reforming, it actually led to higher emissions. So it's not that positive if we're looking for gains in reducing climate impact. This option was not too attractive. Yeah. So you can see how LCA helps us to sort of suss out which alternatives might work and which ones might not. We also looked into break-even mileage. So this is the distance that the alternative powertrain vehicle has to cover in order to have a lower greenhouse gas impact compared to conventional diesel. We find that most of these break-even mileages would take place below the average lifetime mileage. So if you recall, that's about 388,000 kilometers. That's the average lifetime mileage, which is indicated as dashed lines over here. So these charts show the lifetime mileage on the horizontal axis, and on the vertical axis you have the lifetime greenhouse gas emissions. So the gray line here is that for the conventional diesel, and then the alternative powertrains are shown in the colored lines, along with the error margins for the uncertainty that we try to account for in the data. So for diesel hybrids, the benefit sort of grows as you travel more using the vehicle, and the break-even mileage, you hit that around 52,000 kilometers, right? So fairly quickly, we can see that this vehicle can achieve lower greenhouse gases compared to the base case. For battery electric vehicles, it's not so obvious. There's only a slight advantage over conventional diesel, considering the range of uncertainty, as we had seen earlier just now. For fuel cell vehicles, the advantages using steam methane reforming gaseous hydrogen exhibits the advantage also, and we hit that break-even mileage at about just under 100,000 kilometers. So this helps maybe fleet owners think about, for the typical mileage that I tend to rack on my vehicle, when can I hit this benefit? So we arrive at some of the policy recommendations now. So we see that if we really wanted to decarbonize transport, you cannot avoid, examining the accompanying grid or fuel production that's associated with whatever powertrain we're considering. So decarbonizing the upstream fuel production is critical to achieve a lower carbon transport future. If we had limited renewable energy options, like in Singapore's case, I think fuel cell vehicles using gaseous hydrogen, steam methane reforming, as well as diesel hybrids are potential options. Now, fuel cell vehicles would require a lot more investments, right, in the infrastructure to make it available. The market must also be ready before we can deploy this on a scale, at scale. But it can offer, higher greenhouse gas emission reductions up to 25%. So diesel hybrids are maybe less uncertainty involved, maybe less barriers to adoption. You can very quickly, switch your fleet to diesel hybrids. They offer the lowest break-even mileage, clear advantage compared to the base conventional diesel that we're considering. Modest greenhouse gas emissions, though, only up to about 10%, but seems like a straightforward option that many can consider already. So it seems like really we really need to think about cleaner technologies for heavy vehicles. There's a lot of research already underway to think of what these alternatives can be, but we need to have more trials. We need to have some technology pilots, some demonstrations, both involving the research community as well as with industry. I think this will really help push out some of the alternatives that we can consider for these larger vehicles. Most of these technology options are now at the very early stages of development, so we do need to start thinking about investing in them. This is one of my last few slides already. I think we're also just at the tip of the iceberg. Today I spoke about life cycle greenhouse gas impacts for this specific segment of of road freight. Of course, there are many more impact categories we can consider other than climate change. Life cycle costing was not something that I had addressed yet. Recharging and refueling infrastructure is also part and parcel of considering these alternatives. There's a lot of developments with the electricity grid also and potential for carbon capture. So many new technologies and alternatives are being considered aside from the ones that I have described. So future work, we hope to look more into what's called prospective assessment. So not just look at today's situation with today's grid and what are the options in the near term, but we can imagine what the future possibilities might be and account for these future developments in our assessment. So for example, with more carbon capture, what might it be like with a regional power grid that offers more renewable energy options? Maybe that can help us decarbonize also. For trucks, I think I've already described the importance of looking at the use phase and the different contexts that they are used in, but we know that trucks are used by so many different industry sectors in such different ways. So I think it helps for fleet owners to look at the different operations that they are subject to and how might that influence the decision as to which alternative works the best for your fleet. And again, I already spoke about expanding the study scope to look at other impact categories. So beyond climate change, there could be interest in pollution impacts, resource depletion. So there's a lot of concern about critical materials that are used in batteries and whether or not investing in battery vehicles, battery electric vehicles might have a problem over there. So we need to think about that too. Life cycle costing would be of great concern for many fleet owners before they are willing to consider switching to these alternatives, and then again rolling out the availability of infrastructure to accompany these alternatives. So key takeaways, this is my final slide. So I hope you take away 3 things with you today. Life cycle perspective is really helpful to assess the overall environmental impacts more holistically, and we want to avoid problem shifting. So this LCA is a helpful approach. There are many different alternative fuels and powertrains that can potentially help us reduce our greenhouse gas emissions to meet our climate change goals, especially in road freight to consider, but it has to be coupled with decarbonizing the energy system. So these two have to happen in parallel. And the third key takeaway I hope you bring away with you would be to consider that the diversity of new technologies are available, but they're best studied within the context that they are deployed in. So we really have to look at, again, the use context, the market that they play in, the availability of the fuels in the market that you're in. I think this helps us arrive at feasible solutions much quicker. That's it. Thank you so much for taking the time to hear my session today. I hope that we can continue the discussion through the Q&A, and please feel free to reach out to me if you have more questions, and if you ever come to Singapore, drop me a note. Thank you.
Thank you, Lynette, for this great presentation. We will now have some time for a few questions. And I will start with one question. We do have one question in the chat. But I would like to ask if you think it would be interesting to maybe analyze autonomous vehicles are on trend, and there are some studies for autonomous trucks. So do you think it would be interesting to analyze fuel consumption in relation to autonomous and vehicles with a driver?
Mm-hmm. Yeah, that's a great question. Singapore has been looking very closely into autonomous vehicles, mostly for passenger transport. There's some, of course, autonomous trucks within the port areas, within a confined compound that are happening. I think the energy impacts can be very interesting. Most of the autonomous vehicles are electric vehicles, and then that offers some potential for improvements. Again, I think the use context would matter, the kinds of routes that they serve, the payloads that they take on, before we can do a holistic assessment. But I think that deserves definitely a lot of attention. There's also a lot of interest in Singapore, not just looking at the environmental impacts of autonomous vehicles, but even the market acceptance, so user acceptance of the presence of these robo-taxis or robot vehicles amongst us. And it's an interesting time that I think we will experience this transition, right, towards more autonomous mobility. So we've actually been doing some other studies looking at user acceptance of AVs in Singapore, and generally very, very optimistic. So I think people are looking forward to the deployment.
Thank you. We have a question from Jacob. Thank you for the presentation. Did you consider importing blue hydrogen as an option, A2 with CCUs, and why not include in the final analysis and results?
Right. Yeah, thank you, Jacob, for the question. Definitely, there are many different alternatives we could have considered. I think we started out with the set that I had described, but of course, there are many possibilities, like the one you described, hydrogen with carbon capture, blue hydrogen that does not rely as much on fossil fuels, which are attractive as alternative, as cleaner or greener alternatives, like less carbon intensive alternatives. But we had not included them because of the near-term feasibility. Like we're much further away from these options. As I mean, even fuel cell vehicles with steam methane reforming is not even here yet. So that's why we started looking at the more near-term options. But in the longer run, I agree that these are the pathways that can exist and can offer greater savings, greenhouse gas reductions. So we should definitely consider them as well. It's a matter of scope. So it's not that we did not want to entertain it. It's just we have to start with something first.
Thank you. We have another question from Mikhail. Hi, Professor Cheah. I enjoyed the presentation. I'm wondering how the raw material mining and manufacturing of batteries or other powertrain components contributes to the GHG studies.
Mm-hmm. Yes. So that is accounted for. Thank you, Michael, for the question. So that is accounted for in the vehicle cycle scope. So if you recall, in the life cycle assessment, we begin with the scope definition. So under the fuels, the vehicle cycle, we had accounted for all the materials that would be required to make this to be produced, and that goes into all the subcomponents of the vehicle when we manufacture the vehicle. So So the greenhouse gas emissions impact at least are captured there. What this study did not account for, however, is the topics that I mentioned about material criticality or other impacts like toxicity impacts or biodiversity impacts as a result of mining these materials. Those were not yet accounted for. So it was only the greenhouse gas impacts that were accounted for. Just to add some more detail to that, Michael, we also looked at the replacement of the batteries. So it's not just the initial installation of the battery, but subsequently over the long lifetime of the vehicle and how it's used. If the battery needed replacements, it would be accounted for as well.
Thank you. I don't see any other questions. Let me see. We have a Q&A. No. I don't see any other questions, and we can finish later if we don't have. Oh, we do have just a second.
Yes.
Yes, it's just a comment from Jacob. Makes a lot of sense. Thank you. It would be interesting to know where it sits in a future study in regards to his previous question. We have a question from Dan. Hi, Professor Cheah. Thank you for the informative presentation. I would like to ask if the speed is assumed constant.
Thanks, Dan, for the question. So actually, we tried to account for the variation in the speed that was observed in the trucks. So go back to the slide that shows this speed time trace at the bottom right. So through the use of the data logger, we were quite fortunate and were able to collect a lot of detail from the engine, so the engine status and what speed the vehicle was traveling at. So this variation that was observed in the vehicle speed was accounted for in the construction of a drive cycle here. So we can see this how speed varies, sort of accelerates and sort of maintains a certain high speed and then decelerates eventually. So this was subsequently used in our energy consumption model that accounted for these variations in the speed and therefore the total energy required to overcome the drive cycle that was constructed. So yes, so speed was not constant, but it was, and the variation was accounted for. Thanks, Dan.
Thank you. We have a question from Mackenzie. As for alternative powertrains, you mentioned the hydrogen fuel cell truck as well as hybrid diesel. You've shown some comparative percentage for the best emissions. Could you reiterate which type of powertrain you think would show most promise of usage and efficiency?
If we're thinking about, yeah, great question. I think you're thinking about, okay, so which one was out the best? Which one should we consider? Which is really the point of the study, right? So in terms of energy efficiency, which I think you mentioned in your question, actually we're on the right slide because this chart here shows on the bottom right, the energy consumption in terms of megajoules per ton kilometer hauled by the truck over the drive cycle that I just spoke of. So the battery electric vehicle actually offers a lot of efficiency over the use phase compared to conventional internal combustion engines. That's why EVs are so attractive, right? But if we were to look at the overall life cycle impact, so that's slide. The alternatives that seem most immediately viable, maybe easier to adopt by many fleet operators, might be the diesel hybrid. Again, there's a second bar over here, which offers some, I mentioned 8 to 10% reductions in greenhouse gas emissions overall. So it's a subtle difference, right, between energy efficiency versus greenhouse gas reductions. So if we're looking for greenhouse gas reductions, 8 to 10% can be achieved with hybrids. And then again, when we're thinking about today's grid, today's methods of producing hydrogen and so on, then that's where the fuel cell vehicle with the gaseous hydrogen using current methods of producing hydrogen, we can also get further reductions. So that was in the, let me see which slide were we at, like saw the reductions, yes. Was it this one? This was the one that showed the benefits, the net benefits of both diesel hybrids and fuel cell vehicles using gaseous hydrogen. Yeah.
All right, thank you.
Benzie's
Yeah,
question.
that was a very interesting study and great results.